Professor John Thompson from ICTP. He's going to talk about differential geometry and Calabi geometry.
I'd also like to thank the organisers for the invitation, especially Bo and Nathan. I've been set an impossible task by Ray wants you to know everything about Calabi manifolds by the end of the lecture course. And that's not possible, mainly because I don't know everything about Calabi manifolds, so I couldn't do it even if I wanted to. We'll see how far we get. Are there any Argentinians here? Sorry about the rugby. I'm Australian. Okay, so you'll find a little bit of overlap between my course and Nathan's, and probably Bartlett's as well. So what I would like to try to do, is to start off in lecture 1 with some stuff on real manifolds. Basically, what are they? Followed by things like homology, cohomology. Did you see this sideways? No. Let's start here. So real manifolds. Can you read that? It's too small?
Yes, it's
okay, so basically homology. I mean, much theorem. And two other things we'll get to. And 1.5.
Could you write bigger, please?
Yep, 1.5 to 1.8 of the lecture. Part of the second lecture, part of this one maybe, concludes a climb. Something that Nathan will also get to later on in this course, as you saw. The third lecture will be on try on special holonomy. Can you read that?
Yes.
Yes.
Yes, thank you.
Okay. And possibly complex manifolds if we get time. And presuming everything goes according to plan, lecture 4 will be essentially on some very quick notions. I actually don't believe we'll get through all of that, so we'll go into here. So some very quick notions on Calabi and possibly hypercalars. The hypercalar case is important for the guys who are going to be doing duality. Calabi is important for the guys who actually want to do physics. We'll see what we get through. So I'll start here. I'm not just trying desperately to type up lecture notes for this. I've got to 60 pages with a lot of gaps. So they're not ready. Maybe when they're ready, I'll post them. So basically what you need to do is to think of, we'll start with real manifold. And I just want to talk about this words. So we'll start with real. Manifold. So before I give you the definition, let me just say a few things. So basically, these are topological spaces which allow us to get control of functions on them. So if we want to know things about, if the functions differentiable 5,000 times, then it's good to know something about these guys. So this is a structure which is above, this is a structure on topological spaces. If you don't know what a topological space is, don't worry, we'll only need it intuitively. But it is a structure. So a few things, funny things can happen. The same topological space can have more than one differentiable structure. The classic examples of these are so-called Milnor spheres, and more recently, meaning the last 20 years or so, it's been discovered that R4, your favorite four-dimensional manifold, can have what are known as fake differentiable structures, or an infinite number of inequivalent differentiable structures that you put on your favorite R4. So when somebody says that they've given you a differentiable structure, they better tell you which one. Okay? I'm not going to. And there's another famous theorem by Padea, I think, which says some manifolds don't have any. So some topological spaces don't even have differentiable structures. So don't take it for granted. This is a theme that will go throughout the lectures. That is, when we finally get to complex manifolds, we'll discover that there are manifolds which can have complex structures, some which can't have complex structures, some which can have many complex structures, numbers. In fact, in string theory, you'll find that you run into that straight away. When we get to other things like spinors, which Nathan was talking about, there are spaces which do not carry spinors, just can't have them. Some of your favorite spaces don't allow for spinors. So at every point, when anyone says, hey, you've got this, you sure you've got it, right? That's going to be the aim of the game. The main aim of the game, however, is to do the Kaluza-Klein part and talk about a little bit about string theory, in fact, basically about the dimensional reduction of type 2A and type 2B. But we've got a long way to go before we get there. All right, so now I've talked about something, let me give you the definition. So basically the idea is the following. You've got some space. Here it is. This is your space. Call it X. And everywhere you've got open sets. This is what you would have had with topology. And they intersect. The rest of it. And you think that this guy is made of rubber. So you can stretch it. So basically what you're saying is that every one of these open sets can be made nice and flat. It can be made so the dimension of X Bn, the real dimension of X Bn. Then every one of these can be made to look like a piece of R to the n. So basically what it means is I give you an open set, Ui, and I give you a map called Phi, which maps you into your favorite space, which now is Rn. Right? So this guy is over here. And this is called a chart. That combination, Ui, Phi is a chart. You have to do it for all the possible open sets on your topological space. The conditions that these things need to satisfy are the following. One, well, your open sets good to you if you don't get all of it. 2, if you have an intersection of open sets, so in this picture, there's 2 open sets, they intersect, here's the intersection. Okay. Then there's a thing which I'll call phi ij, which is essentially the composition. Actually, you've got to be careful with this because the authors have different numbering conventions on these things. By the way, I'm going to use Nathan's conventions, which 1 is equal to c is equal to 5 is equal to I is equal to root pi. So if there are factors which have gone wrong, blame Nathan, not me. All right, so basically the idea is the following. Here, do that, there, do that. So I'll call this, sorry, can you see that? It's a bit crumpled. But this would be phi j here, and this would be phi I here. And what I need is that the inverse exists, because otherwise I couldn't write this. And if I can take a point in here and I have the inverse, I end up here. It's supposed to be an intersection. But then I could follow that by this guy, and then I end up there. Or likewise, I could start here, take the inverse, end up there, follow the map around, end up there. So essentially I'm getting myself maps between these 2 things. Here, I go around to there. So these maps, so let's give this an order of differentiability, CR. So R is 0 means continuous, R is 1 means first differentiable, R is 2 second differentiable, and so on. So, and this should also be in CR. The phi is in CR. And 3, I create a maximal atlas, so I use the charts. So if I find any phi u anywhere, any phi u which I can construct in here, such that phi composed with phi I to the -1 and phi I composed with phi to the -1 are CR for all I in my indexing set, which was that one there. Then phi u is included. So I basically look for all compatible charts. Just start with a bunch of charts, and then if I can find another chart, I just keep adding it, right? As long as it's compatible. So I'm maximally compatible. That's it. So we've done that for CR. Now we quickly go to the case where R is infinity, so we quickly go to the smooth case. So that's the formal definition, but as I said before, what it really means is that you've got rubber. You've just got manifold made of rubber, and at every point, it doesn't matter how you do it, you just stretch it out, you flatten it, it looks like Rn, and you can do it without ripping it apart. That's it. Okay, so that's the image you should have in your head. So let me give you some examples.
Excuse me, in the definition of maximal atlas, what says that there? I can read the index, the sub-index.
Which where? The maximal atlas. Take phi u, take any chart,
Yeah.
such that phi composed with phi I to the -1, which is already a chart, and phi I composed with phi to the -1 are both CR. Okay? for all I, then it should be in your atlas. And you just keep building it up until you run out of steam. Okay? So here are examples. This is my favorite example. You see it? Point. Point. That's a very nice differentiable manifold that's got what is known as the discrete and indiscrete topology. It's itself. Okay? It's its own chart, essentially. All right. That was for fun. Here's another example. Here's a real one. The n-dimensional sphere. S to the n, which we can define as sitting inside Rn plus 1. You know how to do that.
So, the homeomorphism between the point and the R to the n is not just the point, and the point is closer to the Rn.
So, what would the homomorphism? What Rn would we have? Would be R to the 0. What's R to the 0? It's a point. It's a point to a point. So it's the most trivial case, which is why I was only kidding. But nevertheless, it's nice to know. So we can stick it inside R to the n plus 1. I mean, the one that you know best is this one. Okay, that's S1. Well, the other one that you know best is this one. That's S0. 2 points. And here we go. Trust me, I cannot draw. Okay, that's S2, and so on. But because we've stuck them in Rn plus 1, we're actually already lucky because we can have nice maps. And this way of sticking them in is simply to say that we have the sum of I equals 1 to n plus 1 of xi squared is equal to 1. I'll take you to the units here. It's important to remember that S0, the zero-dimensional sphere, is actually a manifold of 2 points. People have made really terrible mistakes by forgetting that this thing is not connected to 2 points separately, whereas these guys are. And the usual way of, well, one way of finding charts is to start off with stereographic projection. You can do this in n dimensions, but let me just do it in this two-dimensional case. Take a point on your sphere, put a copy of R2 down here, sit this over the origin of R2. So this is the north pole, this is the south pole, sit it on top of O, 0, 0. The origin, some origin, doesn't matter. And now you can map stereographically like that. And this will give you this, as long as I don't include the north pole, if I do this map, I get a big open set, very big open set. The problem with mapping the north pole is I map it to infinity. I can read mine. Map it to infinity. So this thing goes to infinity, which means you don't know if it's over there or it's over there, wherever it is. Okay. So that's one chart. Another chart you could do is to do the exact opposite, which is, and now just map that guy there. And so as long as you're happy with those two charts, life's good. But you can choose lots of charts. You can have fun with this. So one chart is S2 less the north pole, right? And stereographic projection. And the other chart is S2 minus the south pole. And stereographic projection. The manifolds that S2 is important because that's the first example that you'll come across, string theory. The other ones which are important for you are the genus G, Riemann surfaces. Okay, this is another terrible thing in mathematics. Mathematicians are crazy. Mathematicians here? All right. There's one hiding over there. So they use words in them. God knows how they come across them. Anyway, so Riemann surfaces are two-dimensional real manifolds. When you hear a mathematician talking about a surface, however, they don't mean that. They usually mean a four-dimensional real manifold or a two-dimensional complex manifold. Okay? So depending on who you're talking to, these are either called Riemann surfaces or, for reasons best known to these guys, complex curves. What are they? Well, here you go. Two-sphere, 0, donut, genus 1, chocolate icing, very nice. Genus 2, and so on until you get to G. And that just means G holes. Right? You can see those, they're holes there. So a donut is a round object with a hole through the middle of it with chocolate icing on top. It's a donut. That's a genus 1 surface. So is your coffee cup, by the way. Coffee cup has got one hole in it, and that's also, remember, it's made of rubber. You're allowed to do whatever you like to it. So that is also that. Coffee cup is that. Okay? And so on. And these are the only orientable, smooth, I'll talk about orientation just a tick. Orientable, smooth, compact, closed, two-dimensional manifolds. That's a theorem due to Riemann. So, orientable, I'll talk about in a minute. Smooth, we know, because smooth we mean C infinity. We want a lot of differentiability. Compact, basically, means hold it in your hands, it's small. Closed, no boundary, does not have a boundary. Two-dimensional, it's obviously two-dimensional, and it's a manifold because of a nice theorem. So you're going to be sick of these because you're going to be seeing these all week this week, all week next week, and you stay being string theorists basically for the rest of your lives. Let me just say a word about how I'm doing for time, by the way, because I have a real problem with time.
About 5 minutes.
Oh my God. Right, we're probably going to only get through lecture 1 in 4 lectures. Okay, so what do I mean by orientable? I'll give the formal definition, then we'll do some intuitive things later. So, definition. A manifold is said to be, that says we do the word, STB, right? Said to be orientable if for every intersection UI J, not ND, the Jacobian that of these wonderful maps, d phi I, d phi j, x is my point on the manifold. I can take the derivative of these maps this way, and I can ask that it's bigger than 0 everywhere. Okay. How do I know that I can differentiate these guys? Well, I have these phi ij things which connect phi I and phi j, right? So there's a map between them. That's what we said, essentially map between them. So use the implicit function. All right. So that's all I'm going to say formally about these guys. But you all know of manifolds which are not orientable. Mobius strip, do you remember the Mobius? That's not an orientable manifold, so don't take it for granted that you can actually have every space oriented. Yes, I've got them here. So let me give you examples. For real projective space, real projective n-dimensional space are defined by identifying lines in Rn plus 1. So the space will have dimension n, but we're starting, like the spheres. Remember we had the spheres, Sn living inside Rn plus 1. The RPNs will be defined by starting off in a dimension higher, Rn plus 1, without the origin. And what we do is we consider points x1 up to xn plus 1, and we say that they're the same point if they live on a line. Okay. So, roughly speaking, here's can't draw enough arrows, but if you take every line through the origin, then essentially you're going to get something like that, right? You just take the lines. The point being that, well, the points above and the points below have to be identified. So if you take the case of this, about what's going on for RP2. So this line is the same as giving you this better picture. Right, so here we go, R3. Here's your 2 sphere. Like that. Take any line through there, I can, it comes out there, right? So that entire line in R3 is a point. That's what I want. Well, it's the same as if I was looking at S2. This point gives me the whole line, doesn't it? But on S2, so does that point. So every ray is the same as 2 points on S2, but only one point out of every 2. So I've got to identify the 2. So basically I take a ball and I punch through. Antipode, right, through the origin. So I take a basketball and take a point over there and a point over there and just try to push it in. No air in the basketball, otherwise you're not going to do this, so off you go. What it means is that on the boundary you've got this kind of skewing thing going on, and that means it's unorientable. You can just check. Draw some tangent vectors and see what happens, okay? RP3 on the other hand, so this will give me R2. RP3 on the other hand, you know, it has another name. It's called SO3. And that is definitely orientable. And it turns out that n plus 1s are orientable, and the RP2n's are not orientable. So, tangent spaces. Well, I really give you a definition which, if you know it, it's okay. If you don't really know it, don't worry. Here's my manifold X. And take an element, the real line, and just map it in there. There we go. This is on map C. Just got some line in there. And I could parameterize the curve. So here's my open set UI. Remember, I need to tell you which open set I'm sitting in. So I'm in the open set UI, and then I will have some sort of parameterized curve through X, which some X of T. T is the parameter there. So just get some parameter, and then I just follow that through. Phi I is the coordinate chart, so I get a map into whatever the dimension is. I get a mu, so I get a set of coordinates. Is that clear? I worked very hard for that. If I can get it to you by the end of the week, I'll be happy. All right. So what's a tangent vector? Well, a tangent vector is simply, you have some flow, you've got some motion in that direction, just take the derivative, as you would. But really the derivative that you're taking is the derivative of the parameterization of the curve, right? So you get a tangent vector by just looking at the derivative. That's the parameter. I can differentiate this thing with respect to t, and then that would tell me what it looks like in my chart. Okay, well that's nice. But that means I actually need to keep tabs on what's going on with my charts. So the way mathematicians get out of that is they change their point of view a little bit. And the point of view that they take is the following. Suppose I have some function on X. So let's just take it to be into R. Okay. So then I can ask myself, if I have a small vector at X, which I'll call V, for the heck of it, so here I am again, here's X, here's my point, little x, and here's a direction, which I'll call little v, tangent vector to some curve, it doesn't really matter which one. Then some massive theorem tells you that this thing starts off as f of x plus t v mu d mu f of x plus right? And so to first order, right, we want to differentiate this with respect to t and take t equals 0. That tells me where I am. So to first order, I know all about my tangent vector sitting right there. So I will forget the rest of the Taylor series, not interested. And here's my definition. So let's start easily. F is a map from Rn to R, because locally that's what it would look like.
The new index is an index over the x coordinate or over the
X has no, X is a point.
x is a point.
X has no indices. X is a point on my manifold. The only time I get indices is when I take the chart. So the chart has indices, thanks for that. So let's go back to the chart. Okay. you're not interested in what we're going to learn. So here's X. Here's X. Here's my open set. I have a map phi into Rn. Okay? Now it lands in Rn. Here it is. A point there lands there. It's a point in Rn. How do you write a point in Rn? You give it its 1, 2, 3, 4, 5 components, right? So the act. I'll put the I and the I there of X, and that mu is really of Rn. Thanks. All right, so we have such a map. So we define a vector to eat functions for breakfast, and what it produces for you is the following. Sum. System's my notation. 1 to n v mu of f around point P. This is a point P. Sorry, I should have said this is Rn. P. Evaluated at P. And this is in R. Mapping to R. This is basically this. I'm just saying that we're going to be talking about tangent vectors as if this is all that we're, the only part we're interested in. So if I do a coordinate change in Rn, you know how to do those we learned. Then covariant, contravariant vectors transform in the opposite way. And so if I do a coordinate change, which is really what we're doing when we're looking at these differences of charts, right? I've got one set of coordinates, another set of coordinates. We go back here. Ui, uj, points in the middle. I get one patch here, another patch here, and I get a map between them. It's just a change of coordinates. So we know how to do coordinate changes in Rn, and whatever coordinate change I do for a vector and a contravariant, covariant vector, they cancel. And so this is a kind of an invariant way of writing down what's going on. It doesn't really depend on what chart I use. So how do I translate that into a real, into a manifold? The answer is we basically say now if I have f of x, v of f at point P is the same as mu equals 1 to n vi mu phi I of P df composed with phi I to the minus 1 of phi I of B. This is looking complicated, but you'll understand why I'm writing the way this is. Phi I. That's the definition. What is it saying? So here we've got some guy in one of these charts. We've got it over there, right? So I'm giving you numbers in the ith chart. I'm giving you a derivative in the ith chart, so I'm actually in Rn. This is in Rn, this is in Rn. And actually that thing there is also a function on Rn. Because if I get that, the phi to the minus 1 there tells me that I've started over here. I've pulled myself back to the manifold, and then I've mapped myself off to R with the function. That gives me a function which is actually starting from here. So everything that you see over here is happening in Rn. Kind of convenient. But now, a function is a function is a function. So you use that rule. So if I have the intersection of charts, this should really be the sum u equals 1 to n bj u by j of p f composed with j to the minus 1 by j u of p by j p. But this, look at this thing here. This is phi I minus 1 phi I is just, nothing, it's the identity, so it's just f of p, right? And likewise here, it's just f of p. So don't worry about what's going on up here. They're the same. Do worry about what's going on over here. But we're in Rn. And you told me, well, you believed me when I said, providing covariant and contravariant transform in opposite ways, we have an invariant. So actually, these two things are really equal, as they should be. So what it tells me, invariantly, is that a vector should really always be written as the sum u equals 1 to n d mu I xi. So this is the coordinate of the ith patch. This transforms inversely to that guy. And therefore, everything is fine. On intersections, I can just write this as j, j, j. So let me repeat. You'll remember from, this is something that you learned in special relativity, that in the ith patch, the vectors are given in this way. Okay, on the intersection. Just a fancy way of writing the coordinate transformation. And this being invariant is simply saying that v on ui is the same as v on uj when those two things intersect. Moving on. So time. Oh my god. We start at 11?
Yes.
Sure we can start at 11:30? Desperate. Okay, so that's tangent vectors at every point. Of course, I can vary the point, and what I get is a tangent vector field, because vector fields are just the same thing as vectors at every point. So I can construct objects like that. So what I'll do is just give you a bunch of definitions which follow from the logic of this. So definition number 300 is the space of tangent vectors at a point x, big X, is called the tangent space. At x, and is denoted by xx. Okay?
Sorry, this x, y is actually dy and y. I don't understand. You said before the x don't have indices.
Sorry, I've just changed the meaning of an x. X here doesn't have indices, right? Whereas x, where's x here?
Over there.
Oh yeah, sorry, these are just phi j mu of p. I mean, sorry. There's simply not enough letters in any alphabet to do this. So I'm Sorry about that. Okay, so so basically what we've got is we've got point is x. We've got a little point here and here. You've got some vector space. It's a vector space. Remember, tangent vectors are vectors, so it's a vector space, and it sits on top of the point. Right? I've got a point. I've got all the tangent vectors I can possibly think of, and I simply stick them at x. Now we allow this to roam over all points on x. So the tangent bundle is the collection of tangent vectors, tangent spaces. So this is T x equals every point, and now I just take the union. Right? So basically, here's my point x. I put this. If dimension of x is if the dimension of x happens to be n, then the dimension of the tangent space at any point is also n, because I can smoothly, don't forget it's smooth, I can see every direction. So I get an n-dimensional vector space here. And basically what I'm saying is that if I've got an x prime, I can stick the same thing on, and over there, and over there, and over there. So we just take the union of all of these guys and call that the tangent bundle. The usefulness of that notion is the following. It allows you to define a vector. So a tangent vector is an element of this guy. A tangent vector field is an element of this guy. So definition. Section V of tangent bundle of x is a map. So V x to Tx, so it's a map from my space into tangent vectors. At every point I get a tangent vector, right? So think about, so here I want to have the tangent space. So this is almost correct, but I might do something stupid. I might decide to take x, this v of x thing, and map it to this space here. After all, that is inside there. I might do that. That would be damn daft. And to stop me from doing something really stupid, you add one more proviso to this thing, because I need to be told what not to do. So phi composed with v is equal to the identity map, where pi maps the tangent bundle to x in the most stupid way. It maps tangent Tx, x, x. Okay? So that stops me from doing this, taking a map up to there, because then if I map down, I get x prime, I don't get x. That's what that says.
Are there always such vector fields which are defined globally? Or are they suitable right now to do this locally?
Here's one. Don't laugh. Okay. Yeah, you could find vector fields. There are restrictions, but you could find vector fields. Maybe I'll come to an example of where there are some restrictions on the zeros of such vector fields. Okay. Okie doke.
It is a little implicit in the representation of the vector, but maybe you need to mention of tangent spaces and vector spaces.
I think I did, but if I didn't, let me repeat. The tangent space is a vector space. Thanks. All right. So That's neat, and we're already 2 hours behind schedule. So now, once you've got a vector space, thanks for that. That gives me a nice segue. Once you've got a vector space, you also get a dual vector space. So if you remember, what a dual vector space to a vector space is the space of linear maps from the vector space into, let's take the reals, it could be C, but I'm not too worried about that. So the dual vector space is the space of linear maps from the vector space into the reals. The dual vector space has the same dimension as the vector space. This is stuff that you learned in linear algebra. I don't know when. Okay? So I've given you a vector space, so you should now ask me, right, what's my dual vector space? So the answer to that is the following definition. The cotangent space which is usually denoted by Tx and then a dual symbol there, x at x is the dual vector space. Okay? Let me repeat. The dual vector space is really a vector space. It has the same dimension as the vector space you first thought of, and it is the space of linear functions. Very often in physics we tend to confuse these two concepts because we also have a metric in mind. So we tend to pass from one to the other without thinking. However, you can't do that, not really, not globally. So you have to be a bit careful, and so we're going to be a bit careful. All right? And you'll be really shocked to know that the cotangent bundle is given by all the dual vector spaces at every point. And there's also a projection map. So just as we had pi here, we had pi which maps Tx to x, there's also another pi which maps T star x to x, again giving us the point below. Okay, now I'm in a bit of a bind. I don't know what to do. It's a problem of notation. The obvious thing here is to put a pi star there. Unfortunately, that's taken. Let's pull back. So you might like to put the star at the bottom. That's also taken. Let's push forward. So I don't know what to do. I'll just call them both pi. You just have to remember which space you're acting on, okay?
Put it on the left.
Put on the left. Radical. Okay. Thank you.
No, the star.
Hi, I like that. Thank you. What's your surname?
Hmm?
What is your name?
Wilder.
Winter.
Wilder.
Wilder.
Like wilderness.
So this is now the Wilder map. No, I think that's fine. Great. Notation's everything. So these guys, I mean, you know, vectors are covariant or contravariant objects. The duals would be covariant or contravariant objects. Okay, so they just change things. So let me. So if I have a section of this guy, so I have W is a map from X into T star X, and again pi composed with W is equal to the identity map. Then in each open set we have omega is equal to the sum u equals 1 to n xi. And now I'm going to take as a basis not ddx, but dx, and I'll motivate that in a kind of a silly way. you do remember that dx mu, stopping in here, right? Well, the basis for our tangent vectors were these guys. So we could find a basis for the dual vector space to be these guys. Differentials. This gives me a nice basis for the dual space. So remember, these are linear maps. So dx mu, d mu is really what I'm writing here. If the dual vector space is a space of linear maps, I can always find a basis which has this property. I will call it dx nu, and it fits in with your favorite differentiation rule. Okay, so that's where we can come up with the notation. These guys obviously have to transform in exactly the opposite way to the del mu's to be sure that this thing stays true in every patch, and therefore we get the usual transformation rules for the components. Something that you've seen in special relativity again, or general relativity. Okay. Is that clear? So it's a bit quick, but I'm running out of time. And so finally, just to complete my quick whiz through manifolds and GR essentially. Tensor of degree, so RS, is a section of TX tensor TX R times tensor T star X tensor star X S times. And the reason that is tensor is because you know how tensor products work. So in particular, if I write tau in local coordinates, you'll see everything is like it should be. Have mu1 up to mu r, mu1 to mu s of coefficients. So mu1 up to mu r, mu1 to mu s, ddx mu1 tensor, tensor x r tensor x mu1 and in physics, these coefficients are usually what we call the tensors. And they have to transform covariantly and contravariantly to make sure that this thing makes sense globally. And that's exactly the transformation rule that we use. Now there's a special class of tensor. This is a reducible tensor. I mean, if you know very well that if I had just TX tensor TX, then I could decompose it into its symmetric part, its traceless part, whatever. They would be irreducible representations. But as it is, this is a reducible representation. There's one set of reps which are very important for the whole story that we're going to have for the rest of the lectures. These are the differential forms. So basically what I really want to do is I want to look at the antisymmetric tensors of these guys. So antisymmetric so I'm going to just introduce a little bit of notation to cover that. So we say that dx mu wedge, dx mu is by definition 1/2 dx mu tensor dx mu minus dx mu. And from this, you can go on and build up all the antisymmetric bits. So we'll do some of that. Sometimes, and without warning, I'll drop the wedge product. You can check that for the definition. So was there a question? So the definition of a P form is, say, alpha P. This normalization is for later use. As I said, if it's the wrong normalization, you have to blame Nathan. Sigma is in the permutations. And then we have -1 to sigma, so odd versus even permutations. And then we have, sorry, I don't need that yet. I'll come down to that in just a minute. Sorry, this is a little bit too fast. Sum over all the indices, alpha mu1, up, dx mu1, wedge, p, now I need to give it to you. And then dx mu1, wedge, dx mu p is one of p factorial. These p factorials do come up all the time. So permutations, perms. So you take all the possible permutations, the p factorial of them, okay, and p objects, and you sum according to signs depending on whether the permutation is an odd or an even permutation. Okay? So that's what this means. I haven't given you any exercises, so maybe as an exercise you might like to check that, but that's a good definition, right? For example, do it for 2, see what you get. So now we have forms, and I need to define spaces of forms. So zero form, that means there are no dx's. So here, 0 factorial is 1, so we just get a function. So we just get 5x. A 1 form, so I'll write it as alpha, this is alpha 0, so we'll write alpha 1 is equal to 1 over 1 factorial, which is 1, and then we just get a mu. Sometimes I use Einstein's summation convention, so if you don't see the sum there, don't panic. And the 2 form, alpha 2 is 1 over 2 factorial, which is 1 over 2, and then we get b mu, dx mu, wedge, dx mu, and so on. Because these things are totally antisymmetric, the only thing that can appear here from this b is its totally antisymmetric part. So you automatically learn that b mu nu must equal minus b mu nu. And so on for all the higher order forms. You're projecting onto a piece which is only totally antisymmetric. Right. So some definitions. The space of smooth P-forms. Well, these coefficients, we know how they transform, and so as coefficients, they're functions of x, right, point. And if they're smooth, I simply mean that you can differentiate them as much as you like. Right? So that's what I mean here. The space of smooth P-forms is denoted by P, X, and then usually R if the coefficients are real, but nobody said that the coefficients had to be real, So we could also have omega p x c. So the coefficient is complex. So the r refers to these. The r refers to these guys, and c also refers to these guys. Okay, it's got nothing to do with the dx's. I have a real manifold, but the functions I take on them can be complex functions. Nobody stops me from doing it. Now these are vector spaces because if I have a p-form and I add a p-form to it, it's still a p-form. If I multiply it by 0, I get 0. If I multiply it by some other scalar, it's still a p-form, etc. so on and so forth. You can check that these are vector spaces. So they're infinite dimensional because you can have a lot of functions, as you all know. Basically, even for omega 0, there's basically one function for every point on the space that you're considering, and that's a lot of points. So that thing is infinite dimensional. Okay? Same is true with omega 1 and omega 2 and omega 3. They're all infinite dimensional. Can somebody warn me when I've got 5 minutes left? Sorry? 10 minutes? 20. Ah, 20. All right. So here's another wonderful definition. The degree of a p-form is p. That seems like a redundant statement. Nevertheless, it's useful. So now what I want to do is I want to spend some time looking at what we can do with p-forms. How nasty can we be? Well, it can be quite nasty.
When you say degree here, it's also the same as degree in the tensor sense, right?
So that's right. So in the tensor sense, the degree was rs. Now r is 0, and so the degree for the form, I have to think of these forms. Thank you. Thanks. All right, the first thing that we can do is wedge them. So suppose I had somebody p, x, c, and then I wedge it with omega q, x. Right? Well, what I get is somebody who's antisymmetric, not in p, q, but in p plus q. So I have this guy is in here. You can have c here and r there, but then it would end up being c there. Okay? You just have to be careful with the coefficient system. But in any case, you have, so we have a map. So let me write it as a map. So we have the wedge map, which is that.
Question. The degree of p-form is independent of the dimension of the manifold?
Independent. Okay, so suppose you're in one dimension and your p-form has degree 600. It's 0. That's all. So, thank you. Let me explain why it's 0. Over here. So remember, we're taking totally antisymmetric things. So if we're in think locally. If you're in Rn and you want to ask if I've got n objects, because I've got n basis vectors, so I've got dx1 up to dxn. I can never do dx1 wedge dx1, right? That's equal to 0. In particular, if I have dx1 wedge dx3 wedge dx5 wedge something wedge dx1, that is also 0 because these are antisymmetric. I can move that one over there, the minus sign, keep moving it, keep moving it, keep moving it, until I get dx1 wedge dx1, and that is You just told me before it's 0. So you can never have the same label appear twice. So you can never have a differential form of degree. So all forms of degree p greater than or equal to n plus 1 are 0.
I concluded, isn't that a combinatorial of n over p? That's because p can't be over n.
You're counting the number of forms.
Yeah.
Yeah, you're counting the number of forms. But nevertheless, the degree can never be this.
Yeah, but
I'm not counting the number of forms.
yeah.
Yes, but you're right. It's Pn. N, P, depending on what you're thinking. All right. So what does that mean? Well, what it means is, suppose I've got an alpha P form, then I wedge it with a beta Q form. Right, just put the wedge sign in there. Then, to change the order of these things, what happens? I have to take Q of them through P. Right? So I can get the following nice formula. This almost actually defines an algebra. If we restrict the labels P, then it doesn't, because we pop out of the algebra. Where are we? But if we sum over, so the way you get an algebra is sometimes you hear of it, so I'll just write it. Omega star tensor omega star goes into omega star, and so that actually gives us an algebra by wedge product. And this is called Cartan's exterior algebra. And I haven't told you what star is. And star simply means that I sum over everything in sight. So the direct sum of vector spaces, starting off with the lowest one, I add to that the first one, add to that the second one, and so on. Okay? All right. So one thing I need more maps. Sorry, we don't have enough maps. We need more maps. So let me give you another map. Find the exterior derivative. So we have D, which acts on space omega p x. It takes us into omega p plus 1 of x. And the definition of D is kind of clever because it mixes the cotangent bundle with the tangent bundle. And so it's this. Okay. So this is the D operator. As you can see, it's a derivative operator, but it obviously does this. So I'll just give you a few examples. So is this well defined? This depends. These are local coordinates, so it depends on the chart. Same argument as we've used before, right from the very beginning. These transform in exactly the right way to cancel the transformation of these guys on overlaps, and therefore this is a well-defined operator on the manifold. So, with that, let's act on alpha 0, and we get the sum x mu, d mu, what do I call it? Phi. Phi. This is obviously a 1 form. I promised you that if I put 0 there, I will get 1 there. How about d alpha 1? Well, I am told to do the following. Mu sum dx mu. this is only supposed to act on the functions. So this becomes the sum over mu and nu, and then I get d nu a mu, and then I have dx mu wedge dx mu. That's the map. And another way of writing that is as 1/2, or this is the sum of mu, if you like. Field strengths, this is F mu nu. And this is a 2 form. And so on. There is one property of the D. So here we said wedge. So wedge is a map from omega star tends omega star to this space. D can be thought of as a map from omega star to omega star, because they both of these things live in omega star, so you can think of it that way. The property, which is actually crucial, is the following. Okay, maybe one thing before. I have to tell you how this works. So, you have your favorite rule for differentiating.
Rule?
Huh?
Leibniz rule?
You have your favorite rule, Leibniz. So, if you're German, and you write, this so far so good, right? And now what you want to do is you want to write alpha p wedge d beta q because of the derivative, but you must remember that you've carried through a dx mu, and it's gone through p of these guys. There are p in there. So every time you go through one, you pick up a sign, you have p signs, so it's plus minus 1 to the p, right? That's the Leibniz rule. Okay. And one thing that you should check, this is your exercise, prove d squared equals 0. Absolutely essential to everything that's going to happen, so somebody should prove it.
Wait,
Preferably.
you use the same argument to say that it was minus 1 to the PQ in the over there, and now it's just minus 1 to the P.
Yes, but I haven't actually, here I changed the order of the beta and the alpha. Here I didn't change the order of the beta and the alpha. Right. To move the beta through the, so there are Q of these guys. I moved one of them through P times. Move the second one through P times. Move the third one through, you getting time?
You did that.
Yeah, that was it. So, all right. So, we tend to say this is nilpotent. Actually, physicists are more prone to say it's nilpotent than mathematicians, but that's what we mean, disgraceful. So, the beautiful thing about the exterior derivative is once we've decided to live on the space of differential forms, D keeps us on the space of differential forms. It does not move us out. We're still there. And it has another great property which I will not prove, which is called Stokes' theorem. So to give you an idea of how Stokes' theorem might go, let's have a look at alpha 2. And let's just think of it as, so on a disk, say. It doesn't really matter. So on a disk, a two-dimensional disk, what's the only thing I can write down in 2 dimensions? Dx dy, right? Dx dy. What's a volume form in 2 dimensions? d2x, which means with a suitable interpretation, dx dy. So the first thing that we learn is integrate forms. I'm not going to tell you how to integrate them. You have to do it properly. I'll write invariant formulae, but I mean, obviously what I would mean really is that you map onto, use your charts, integrate there, pull back, do whatever you like. But invariantly what you're doing is you're integrating on the space that you thought of. So if I'm going to put a form here and integrate it, I need to have enough dx, dy, dz, dw as the dimensions. What sort of form is that? Volume form. It's the highest degree form we have. It's alpha n. Yes. Ah! Nathan finished late. Give me another hour, please. All right. So in our notation, so if we take a form exy, that was a 2 form that I rubbed out before, then in 2D you would say, oh, that's easy. This would just be bxy, dx, dy. There are differences between integrating with forms and with measures, and that has a lot to do with this little orientation, but I'll try to come to that later. So we can integrate a 2 form on a 2 disk. Okay? What does Stokes' theorem say? Stokes' theorem has many manifestations, but in terms of differential geometry, it only has one. So we learned it as Green's theorem, Stokes' theorem, somebody else's theorem. In differential geometry, if you take the derivative of an n-1 degree form, you have a n degree form, right? This we can integrate because this is n-dimensional. That's what we were just arguing over there. So this makes sense. Stokes says, derivative. Total derivative means if x has a boundary, so this is the boundary of x, and alpha n is smooth. I repeat, we're using smooth forms. If it's not smooth, this is not true. If it's smooth, then this is right. Now, if you've got the boundary of the space, what's the dimension of the boundary of the space? 1 dimension less, right? So the boundary of an interval is 2 points. So point. Semi-infinite interval. 1 point. So the dimension of the point is 0, the dimension of the line is 1. You drop 1. If you take a cylinder, I'll take a disk. We've got the disk on the board. Take the disk. What's the boundary of the disk? The circle. That's dimension? 1. Okay? Complain to me later. Dimension 1. And the disk has got dimension? Thank you. Somebody said 2. Somebody said 5 as well, but we won't count that. So this is Stokes' theorem, and it covers the examples that we know in first year calc, second year calc, whatever it is. So you can check, because if you take, for example, on the disk, you try this, and you just do it by hand, you find indeed that you can write the thing. All right. Now my 5 minutes are up, I guess. Yes, my 5 minutes are up, and we're nowhere. So I'll stop and continue tomorrow. Any question?
Question. You mentioned earlier before that the real projected plane of dimension 3 is essentially SO3, the rotation group. Is there some simple way to see this?
Yes. You were doing spinners just 10 seconds ago. I remember. I was watching. What's a two-dimensional spinner? It's a representation of?
SO3.
No.
Two-dimensional.
SU2.
Well, it's a spin representation of SO2.
Yes, it's a
of
spinner
SO3.
representation. So it's an SU2. So SU2 topologically is just S3, and SU2 mod Z2 is your favorite manifold, SO3, but that's S3 mod Z2. I said what you have to do is take the sphere and identify antipodal points. That's Z2. So that's the easiest way of seeing that SO3 is nice.
Thank you.
One question. Why do we study I mean, sorry. Let me think about it.
It's okay, I'll think of an answer.
Any other question?
In visual start integration, you say you have a region, but in the first, in the beginning, the manifold is closed, no boundary. When I integrate in this is zero.
Thank you. So yes, that's right. Great question. So if the boundary of X is 0, or the null set, okay, this thing is 0. Yeah, so I didn't do, I mean, there's enough time to do everything, so you just sort of have to wing it when you say there's a boundary. There are a problem with signs here. I haven't been very honest with you. For example, if you integrate a long curve from 2 points, so we'll call this X and Y, and you go from X to Y like that, and then well, this is a one-dimensional integral, so I have to integrate a 1/4. If I want to use Stokes' theorem, then I should differentiate something, so I have to differentiate a function, so I'll differentiate a function, right? So df, and hang on, you know this, I mean, you really know this, right? Do you really know this? Yeah, this is f of y minus f of x, isn't it? And you notice that I've smuggled in a sign. Yeah, well, this is this orientation business. So you notice that the tangent vector, if that's the direction of my curve, the tangent vector here is going away from my point, whereas the tangent vector here is going towards my point. So there are rules for how to define orientation for boundaries. So depending on who you are, you may have inward normal first. This is the normal to that point going inwards. You might have outward normal first. This is a convention, which basically changes the overall sign of this. But I haven't been careful with signs. I'll try to be careful with signs when I need to be.
More questions? No, thank you. We'll go back after lunch. The afternoon session.
Where are they making the rock?